Hi everyone, my name is Sveta and today I'll present Sparkle. It's a framework that combines reinforcement learning with large language model feedback to learn partial order action plans. So in many real-world tasks like cooking or robotics, we don't have labeled constraints for what should happen and when, yet we still expect intelligent agents to understand what sequence makes sense. So the question I explore is, can an RL agent learn a valid, flexible action sequences using only high-level LLM feedback without any labeled precondition and handcrafted models? So just to understand why I started to think about it is that there's three key challenges that I was focused. First, reinforcement learning has traditionally relied on dense, frequent rewards, but in real-world tasks like cooking, help desk systems, or robotics, feedback is often delayed, sparse, or only available after the entire sequence is completed. And that makes learning hard. The second is procedural domains, like recipes and workflows are full of soft rules. The ordering is not always strict. Some actions can be swapped and other must come first. So these partial order constraints are often not labeled or easy to write down. And the finally is LLM gives us a new opportunity. So they may not tell us exact constraints between the actions, but they might judge whether a sequence of actions makes sense and reach some specific goal. So this raises questions, can we use LLM as a high-level judge guiding an RL agent learning process? So this concept is not really new, especially LLMs. Everyone's trying to use them and leverage them to different tasks. So I was inspired by a few papers. The first one is this paper shows that LLM can be used to generate reward signals in environments where we don't have a predefined reward function, and it's a core idea that I also rely on. This work is a distinction between learning from human feedback and AI feedback. So Sparkle builds on that idea, but instead of fine-tuning LLMs, I use them as feedback during reinforcement learning. And there's here two additional papers, and I will concentrate only on the goal recognition as reinforcement learning. This older work connects RL and plan recognition, a space I build on directly. This is the final goal of this project, but instead of assuming a symbolic planner, which is usually done in planning, I explore goal and plan recognition via learning cue values and natural language feedback. So here's an overview of the environment that I build. So the environment is based on structured procedural task, making pancake, for example. And this task I take from Captain Cook 4D dataset, which includes tokenized steps. So this environment is built on the goal and bag of actions. I will show you later in the next slide. And our agent is a DQN that learns directly from action embeddings. And it's derived from a language. Well, this embedding is basically derived from BERT. And rather using traditional state encoding, we treat past action as a current state. So basically, every action that we are doing, it's accumulated to a state, and it's like generates a new state. The feedback model is a large language model, GPT-4o, which scores full sequences, essentially serving as a sparse but high-level reward function. So instead of regular reward or reward shaping, we're getting our reward from the LLM feedback for the entire episode. And we use Monte Carlo style reward propagation, which discounts the final score back to the sequence to update earlier actions. And ultimately, the goal is to extract a world model from learned behavior of the agent. that support explainable plan and goal recognition even when steps are out of order. So basically, once the RL agents is learned or finished to trained, we can extract the world model, basically the constraints between the actions, what actions have to come before what, in what states, and from that, once we extract into the domain model, we can use it for plan and goal recognition to explain, to have better explainability, to have better plan and goal, or just to recognize out of order plans. And here's an example of the Captain Cook 4D. So here's a graph which has basically the goal here, blender banana pancakes. And here's different actions that connected to and building this procedure of generating banana pancakes. What I use basically, I don't use this graph, I don't use this constraints at all. Only I take the goal and the bag of action without the constraints, without the connections. And this serves for the building the environment. So there are a few challenges that I encountered through the development. And so the first one, since the LLM provides feedback only at the episode level and not per step, the reward signal was very sparse and occasionally noisy, and small mistakes weren't always penalized, which made it difficult for the agent to learn precisely where things went wrong. So yes, sometimes LLM says that the episode is good, although it's not. And the second, the agent tended to overfeed on the initial good transitions. Without enough exploration and sensitives, it kept generating similar actions sequences, failing to discover new variations. So basically what I did, in order to initialize the agent with some kind of good examples, I took this bag of actions, generated a lot of episodes, took it to LLM, it evaluated, and having this buffer of good episodes, which I inject constantly to the agent in order to keep and remember good episodes and good transitions between the states. So here's an example of bad transition, and LLM says it's okay. So for example, here's the sequence of creating pancakes, but pay attention here that the sequence is having first cooking the mixture before pouring the mixture into the pan, and it says and the LLM feedback is that this episode is okay, and it's also gives the explanation. The sequence is logically structured and follows the necessary steps. So for instance, here's the noise that LLMs enters to the system. So the first challenge, I found that the way I represented states by taking last action as state representation. So as I said, my state is basically a accumulation of actions that already been taken, and I constantly took just the last state, just the last action as the final state, which is not really representing the sequentiality that I really wanted to have knowledge about, like to give it to an agent. And it often led to similar sequences having almost this indistinguishable representation, which confused the agent. It's reasonable. And finally, I struggled with a balance between learning constraints and enforcing them. What I mean is that, should I let the agent learn not to repeat actions or explicitly mask them? Most of the cases, when an agent is generating an episode, it's generating repeated actions that are already taken. And I try to figure out whether I would like it to learn, and I will penalize it for that, or I'll just make it as a constraint and I won't even allow him to generate these kind of things. So this is the challenges that I had. So to handle these things, so the first thing is handling sparse rewards from the LLM, I use Monte Carlo style propagation and distributing the final sequence reward backward across all the transition, not only penalizing the last state and the action, but all the states and all the actions. It might be problematic a little bit, but this is what I initially did. And this gave earlier actions some learning signals even when the reward came at the end. And to reduce the overfitting and encourage more exploration, I used epsilon greedy strategy and made this replay buffer focus on recent transitions. So basically, I have a buffer with good episode and I have a buffer that the agents constantly reproduce, like generating. And I wanted that this buffer of the episode will be updated. So I'm constantly like updating with new episode, and I mix between the good episodes and the one that the agent is generating constantly in order not to forget the good ones, but also to teach and train the agent itself. I experimented with different state encoding strategies. Initially, I used mean pulled BERT embedding over past actions, and later I added normalization to improve contrast between similar looking action histories. And I have to say that it's something that I forgot, but normalization, when it enters to neural network, is always something very good to remember. On the constraint side, I debated whether the agent should learn to avoid invalid actions, as I already said, or to enforce. I tried both ways, but for now, I just I decided not to give it as a hard constraint. I wanted to learn it. Maybe it's a mistake, but I will see. And finally, I built a set of diagnostic plots. So yeah, so it's a really good thing to have good plots in order to understand what's the state of your training. So here are a few results. So first of all, the results that you can see here from the left is the embedding of the states. And I wanted to make sure that the embeddings is basically all the states are not just located on one space. We can distinguish between them. This is a t-SNE representation. And here's something is a Q values that the agent already learned for state 0. So what does it mean? From the right, you can see that this is the bag of actions that the agent have, that the environment basically have, that the agent have in order to generate an episode. So what I want to see that in state 0, the only action that it can make is the yellow ones. I wanted to make sure that it learned that. So how it can learn it from the good episode that I already introduced it for. So I don't want it, of course, to forget them. So as I said, I'm mixing good episodes and the one that the RL agent is just generating. And after a while when it's trained, I'm checking the Q values, and I can see that the high values are for the good actions that the agent can take, are the valid actions, and the negative values of Q values are for the actions that the agent cannot take. So it's a good sign that my agent is learn something. Another thing is the loss over time. I can see that the loss is converging. At the beginning, it has a high epsilon in order to explore different actions and to enter to different states. But after a while, it converges really good. I have also Q values and target values. So my next steps. At the end, I still struggle with training this agent because although in state 0 we can see that I managed to train it, but at the other states there's still they are still noisy and they are not converging. I suspect that it's something that relates to the architecture that I use. But here are the next steps how I plan to tackle this problem. So increase LLM feedback coverage, relax repetition penalties to allow longer episodes, and I also want to have entropy and action diversity. It's something that will help to an agent not to do repetition for the same actions. And there's a thought about use curriculum. Maybe I need to start from short plans and then to get them longer. And of course, as I said, the architecture. I suspect that probably the architecture that I use, I want to switch it to LSTM. Meanwhile, it's fully connected. I know it's probably not a good idea at all, especially when I want to learn some procedure. So I plan to change it to LSTM. Anyway, thank you for listening.